Okay, here we have a review question from series circuits. So I'm just asking you to find each of the following values that are below. So I kind of wrote in these subscripts here. So this one is V total. So that's the total voltage of the circuit. V1, V2. Oh, I left out V3 here. Oh well, let's put it in over here. And that would be the voltage over resistor 1, resistor 2, resistor 3, and then I1, I2, and I3. Okay, so V total is pretty obvious. V total is going to be 120 volts because it's the total voltage the circuit has. Now, before we move on to V1, V2, all that stuff, I want to next do R total. Okay, so R total is just a straight sum of them. So you got 20 ohms, 5 ohms, and 15 ohms. So those add up to a total of 40 ohms. Okay, so now I have R total and V total. Now, remember that the current that's going through this circuit is the same everywhere in that circuit. Okay, so if I know I total, I know I through 1 and 2 and 3. So my next goal is going to be to find I total. So I'm going to say V total equals I total, R total. So V total is the 120 volts. R total is 40 ohms. I'm looking for I total. So what times 40 gives us 120 rather? It's 3 amps. 3 amps. So we got 3 amps, 3 amps, 3 amps. Okay. Now, in order to find voltage drop across 1, 2, and 3, now we're just going to do V1 equals I1R1. So we're looking for V1. I1 is 3 amps, and R1 is 20 ohms. So V1 is going to be 60 volts. So over here, say 60 volts. Okay, then we're going to start with V2, I2, R2. So V2 is going to be the same 3 amps. It's the same everywhere. Now we're only looking at 5 ohms. So that's 15 volts. So this is 15 volts. And then, just to keep it, I guess the same way as we've been doing it, I3, R3. So we got V3 equals 3 amps times 15 ohms. So that's going to be 45 volts. Now, just to make sure that our voltage rule holds true, we know that it's supposed to add up to 120. We get 60 plus 15 is 75. 75 and 45, nicely enough, is 120. Okay, now, I just wanted, before we move on to the next thing, I want to just talk about something from the lesson I did yesterday. So, the lesson yesterday on devices discussed hooking up voltmeters and ammeters. So, if I wanted to hook up a voltmeter here, let's say I wanted to find out the voltage across this guy, voltage across 1. I'm going to hook it up so it's hooked up on either side of this device, so that it gets a measured voltage beforehand and afterwards. So, beforehand, the current came out of here with 120 volts, so it gets here with 120 volts. Now, we just calculated out the voltage across this guy to be 60. So, what we're really finding, remember, is the voltage drop. So our voltmeter is going to read 60 because that's how much is getting lost. In which case, we're going to be left with 60 on the other side. So the current that leaves here only has 60 volts potential. If I put a voltmeter here across 2, now we know the voltage drop across that guy is 15. So that means that we're losing 15 across here. So if I got here with 60, and I lost 15, I have 45, which, thinking about it this way, makes this guy a lot easier, because how much does he have to have before he gets to the battery? He has to be at 0 when he gets to the battery, which means he has to be 0 here, which means he has to lose all 45 over that last resistor rather. So hopefully that makes a little bit of sense for us. So here's what we're going to get into today. It looks a little bit more complicated. So a parallel circuit. A parallel circuit is simply a circuit that has multiple, or they call it parallel, paths for current to flow. So I'm going to get my colors changed here while you get a chance to write this out. Okay. So we have a voltmeter, or rather a voltage source. It's hooked up, and it basically makes these two little loops. So we got this loop here. So basically what it means is current can come out. Let's do it a different way. The current is going to come out of the battery. From here to here, it has nowhere else to go. This is like a series circuit. Now, when it gets here, it now has a choice. So it could either go this way, up in this loop. So we'll call that the current just in leg 1 associated with resistor 1. Now, if it doesn't go that way, it would go this way. Okay, so you got total current coming out of the battery, some of it. So if you think of this as a grouping of electrons, some of it's going to go this way, and some of it's going to go this way. So what happens is when you get here, it splits into 2 pieces, or 3 pieces, or 4 pieces when we start getting the more complicated ones. Now, when it gets back here, well, the current that's going up this way and this way, just like water currents would be, this guy coming up from 1 isn't going to double back, nor is this guy going to double this way. So when they both get here, they're going to combine back together, and they're going to go back this way. Now, you note that I made it purple again, because if I1 and I2 get back together, they're going to be I total. Okay? So this is going to lead us to our next rule. Okay. I total equals I1 plus I2 plus I3 plus ... Okay? That means that if I take the current going through each leg, there are more of them, and I add them up, I will get back to my total current, the current that came out of the battery in the first place. Okay, now, this next one is a hugely important thing for physics. It's a hugely important thing for series circuits. It's one of the reasons why parallel circuits, it's one of the reasons why parallel circuits are by far the most commonly used in all households. Okay, so we got current coming out here, right? So what we're going to look at, and the reason why I'm using the red pen right now, is because we're going to think of the electrons that come out of the battery, get to this juncture, and choose to go up leg 1. So the red one is going to be the current going through just leg 1. Okay, so we're going to, for now, kind of pretend this doesn't exist, because we're looking at just the electrons that left the battery, came up through this resistor only, and went in. Now, if we're looking at just those, they have a voltage of V coming out of the battery. So if this was, let's say, 100 volts, right? That means that when the current comes across just this resistor, and it's only ever encountering this current, the electrons that choose to go this path are only ever encountering that resistor. That means that they have to lose all 100 volts of the voltage they're given over this resistor before they go into the battery. Now, if we switch to looking at just the current that goes the other way, so let's see the current that came out of the battery got to this juncture, and instead of going up that juncture went this way and all the way back in. Well, that blue current that I just drew here is only ever going to encounter that resistor. So it had 100 volts of energy to give away. It runs into that resistor, so it's going to drop all 100 volts of itself, or of its energy rather, over that resistor before it comes in. So, why is that a really super important piece of information? Well, for one, it makes our rule much easier, because our total voltage rule is just going to be this. So whatever voltage you have for the battery, that's going to be equal to the voltage that gets dropped across leg 1, which is equal to the voltage that gets dropped across leg 2 and leg 3, and so on and so forth. Well, this brings us to the idea that you've probably heard about before, or maybe if you ever heard that whole 12 Pains of Christmas song. If you set something up in parallel like this, so let's say each one of these resistors represents a light bulb in a string of lights. If things are hooked up in parallel like this, if this guy stops working, that's fine, because the current is still going to leave here and still going to go to this one. It's still going to get the full 100 volts. So let's make it easier. Let's think about in your house. If your house was hooked up in series instead of in parallel, so let's look at this. So if we hooked your house up in series, and this was your TV, and this was your lamp, and all of a sudden your TV started not working anymore. Well, if your whole house was hooked up in series, that would mean that no current would get here because it can't get past here, which would mean suddenly your lamp would go out. But we all know that's not true. When you turn your TV off, your lamp could still stay on, right? Why is that? Well, that's because your house is hooked up in parallel. So your TV is getting the full 120 volts sent to it from the panel in the basement. So your TV is getting the full 120 volts. Your lamp is getting the full 120 volts. Your hair dryer, whatever it may be, they're all hooked up on their own circuit. So if you shut one of them off, the other two are still getting the full voltage. Okay. We'll talk about that more probably end of the week next week, but I just wanted you to kind of see why it is that they make these parallel circuits other than just to confuse high school physics students. Okay. Now, we're going to go back to this slide. I'm going to neaten it up a whole bunch. Okay. Let me get rid of some of this. And we have a rule for current already. We have a rule now for voltage. Now we have to come up with a rule for resistance. Now, this one's not quite so simple. So we're going to say V equals IR, because we know V equals IR. That's our friend forever. All right. Now, we have a formula that says I total equals I1 plus I2 plus I3 plus ... Now, we don't want a formula for voltage. We want a formula for resistance. So here's what we're going to do. We're going to get rid of the current by putting in what it's equal to. So we're going to say current is equal to V over R. So I can write this guy as V total, R total. Now, bear with me. There's a reason why I'm leaving gaps here. So those of you guys who love taking good notes, and you know who you are, we're leaving gaps purposely. Okay. Now, this is better because it now has resistance in it, but we don't want a formula that has resistance and voltage in it. We want a formula that just has resistance in it. So, what am I going to do? I'm going to divide, or I'm going to multiply, I guess, this side by 1 over t. Get rid of that, and we have just 1 over RT. But remember, if I'm going to do that to one term, I have to do that to every single term. Now, remembering our other rule, which was the voltage across here is equal to the voltage across here, which is equal to the voltage across here, or V total equals V1, V2, so on and so forth. That means that these cancel out, and these cancel out, and these cancel out, and so on and so forth. So what we end up with, we end up with a formula that says 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... Now, before you get into it and say, well, how is that any different than RT equals R1 plus R2 plus R3? Isn't that the same thing? No, got to be careful because the sum of fractions is not the same as the fraction of the sums. Or let's make that a little bit simpler. If I said that R1 plus R2 plus R3. So let's say we have 3 resistors, and I let each one of them be 2. Well, this sum would be 6, right? Now, how would we do that in this case? It would be 1 over R total equals 1 over 2 plus 1 over 2 plus 1 over 2. So that would be already significantly different because we got 1, 2, 3 over 2, 1 over our total. Now, you could do one of two things from this point. You could flip and multiply. Rather, you can cross multiply. Or since this is 1 over RT, you could just say that RT over 1 is just the inverse of this guy. So if I flip this, I have to flip that. So my total resistance for this setup of 2 of these guys, or 3 of these guys with 2 ohm resistances would be that. Okay. So let's just really quick before we get into any examples, look at this. On your reference table, it gives you these rules. So just like with the series circuits, we don't want to start panicking because they give us these rules. Now, they don't write I total, but that's basically what this is. This is I coming out of the battery. Okay, this is V total. Now, R equivalent is the same as R total. So if you want to even change that out on your reference table, you can. So these two are reasonably simple rules. This one looks more complicated than it is. As we do more of these, you're going to realize a lot of times you can avoid even having to do this math. But sometimes you're going to have to do it. So let's try an easy example, shall we? Okay. So in this situation, I have my total voltage. I have R1 is 20 ohms. R2 is 50 ohms. Okay. So I'm going to put some subscripts down here. We're going to say, what is V total? What is V1? What is V2? And then I'm going to say, what is I1, I2, and I total? So again, I1 is just going to be associated with the current through R1 and through R2. Okay, so V total, real simple. V total is the voltage of the battery, which is 100 volts. Now, if I know V total is 100 volts, then we know that the voltage drop across R1 and R2 also have to be 100 volts, right? Because this is leg 1 and this is leg 2. They have to have the same voltage as this. So that's going to be 100 volts and 100 volts. Now, current 1 and 2 and total. Now, current 1 is going to be the current through leg 1. So we're going to go back to our good old friend, V equals IR. we got V1 equals I1 R1. So we already said that V1 is 100 volts. We're looking for I1, and R1 is going to be the 20 ohms. So I1 is 5 amps. So we come up here, this guy's 5 amps. Okay, now for I2, we're going to say V2, I2, R2. So V2 is once again 100 volts. I2 is what we're looking for, and R2 is 50 ohms. So this guy's going to be what? 2 amps. Okay, so once I know I1 and I2, I total, remember the rule for I total, is it's the sum of the currents through each of the legs. So in this case, there's only 2 of them, so it's going to be 5 plus 2, which is going to be 7 amps. Okay, now, you note that I did not ask you for R total here, so let's talk about that now. So to find the total resistance, there's 2 different ways of doing it. Now, let's do this way first. 1 over R1 plus 1 over R2. Okay, so 1 over R total equals 1 over 20, because that was the resistance of R1, and 1 over 50. Now, let's remember our basic math. We need a common denominator here. So, that 1 over RT, our common denominator would be 100. Oh, it's not the right one up there. Our common denominator is going to be 100. So that would make this 5. 100. So that would make this 2. So 1 over our total is equal to 7 over 100. Now, that's not quite the answer yet, because that's 1 over R total. So what is R total? Well, if I flip this guy to make him R total over 1, I have to flip this guy. So he's 100 over 7 ohms. Now, a lot of times I'm going to suggest you maybe leave it this way. If you want to make this into a decimal, you can. It's going to be 14 2/7 ohms, if you really must do that. But either one of these is fine. Now, I said before that there's a way of getting away with not doing this math, and there is. So we're going to say V equals IR, but we're going to do it for the totals. So V total is 100 volts. I total, well, we know I total is 7 amps. We found it before. And R total is R total. And with some algebra, R total is 100 over 7, which is exactly what we got here. So it's 2 different ways of doing the exact same thing. Okay? Let's try another example. So what I've done here instead is I wrote them up here just to make up less room. And I brought in these devices. Remember I talked about the devices in the beginning. I talked about them in a small video yesterday. This is voltmeter 1, which is going to measure the voltage over 1. This is voltmeter 2, which is going to measure the voltage drop across 2. And that battery is V. Okay? So what we have here, what I'm looking for here, is just, again, some simple enough questions. So V2. Remembering that the voltage drop across this guy is 200. Now what we need to do is we need to just work backwards. If we know that the voltage drop across here is 200, we know that that means the voltage drop across the battery must have been 200, because these 2 things have to be equal. And therefore, the voltage drop across here also needs to be 200. So this is going to be 200 volts. This is going to be 200 volts. Okay? And obviously that's 200 volts. Now, current through 1, we can once again just say V1 equals I1 R1. So 200 volts equals I1. And R1 I have written up in the top corner there is 40 ohms. Okay. So that's going to be 5 amps. Okay. Now V2, or certainly I2 rather. So we got V2, I2, R2. So this is 200 volts. Looking for I2. R2 is 60. Okay, so I2 now turns out to be this weird fraction. Well, not an incredibly weird fraction, but it's going to be 3 1/3 amps, or 3.33 repeating. Sorry, I guess I should have said that. I was trying to give you guys some time to look at that on your own. And now I total is going to be, well, 8 1/3 amps. Okay. So last thing I want to talk about is just a concept you absolutely need to know. All right. There's really two concepts wrapped up into one. Now, what I'm doing here is I'm doing something reasonably simple. I'm making both of these 10. Now, what I want to do is I want to find out what the total resistance is here. So we'll just do it really quick like we did before. 1/10 plus 1/10. 1 over R total equals 2/10. So R total is going to be 10 over 2 or 5. Now, what does that tell us? What that tells us is two things. One, that our total is less than either of the originals. If you look back at some of the other ones, so let's look at let's look at 2 of these ago. Okay, our total ended up being 14 2/7. That was smaller than the 50, but it was also smaller than the 20. So some very important information we get out of here. And this is a really important fact, so I'm going to write it in red. Okay. Now, our total in parallel is always smaller than the smallest resistor. This is really important to know because this is going to come in handy when you're asked a multiple choice question on this. They could have given you this question and said the equivalent resistance of the circuit is, and they could have given you 5, 10, 20, and 100, just making up numbers. And just knowing this fact on the bottom, knowing these are hooked up in parallel, you could have gotten rid of this guy because it has to be smaller than the smallest one. And since those both are 10, it has to be that. And then those would obviously go away too. So you would be left with having to be 5. Okay. Now, I understand I threw a lot of information at you in this lesson. And I very much assume that some of this will be confusing. So I am going to post an assignment for you. I'm not going to post a very large assignment for you, maybe 10 to 15 questions, because I really want to be able to pull them apart when we meet on Friday and discuss them one at a time, okay? So just kind of what I was saying. So my final thoughts here. I understand the topic is, relatively difficult. So we're going to stop pushing forward after this practice, and we're going to do a lot of questions on just the 2 different types of circuits. So we're going to go back and we're going to revisit series circuits, talk about parallel circuits. We're going to talk about the pros and cons of each one. There'll be a lecture probably Friday about the comparisons between series and parallel. I'm also going to be posting on the website, or I'm going to post on the Google Classroom, a link to this website that's going to allow you to virtually set up some circuits. So it allows you to kind of paste or rather pull and drag pieces of circuits from a bar on the side and create your own circuits. It's going to kind of be a lab-like scenario, because the cool thing about this is it allows you to set up a circuit and it's going to tell you whether or not it's not flowing. Okay, so I'm going to post this, tomorrow I'll post a set of specific circuits that I want you to do. So I'm going to post this, let you guys have a day to just kind of play around with the website. Tomorrow, so Thursday, I'm going to post one or two, description of a circuit that I want you to try to set up. Okay? I want you to set those up. Then I'm going to ask you some specific questions about those. I want you to come on Friday prepared with answers to those questions. That's a terrible underline. Okay, so hopefully we all understood that. If we didn't understand that, I have no problem spending a nice amount of time going over the questions, going over the lecture, whatever it is you guys need to do on Friday to make sure you do understand that. Hopefully we're all getting by here. And, as always, smile. Could be worse. All right?